I'm going to go ahead and cover all of Unit 4 in one video. I think this is a pretty fast, easy topic with a lot of review, stoichiometry. Certainly we'll need to practice some with our net ionic, but I think this is a pretty straightforward unit. So if you think back, this was one of our early units that we spent quite a bit of time reviewing from first year chemistry. We did the copper cycle lab, we did a bunch of stoichiometry, we did a lot of practice with net ionics. So basic stoichiometry review has never changed from first year chemistry. You have the mass of reactant, or moles, or whatever they give you. They could give you molarity. Whatever you get of that reactant, you're going to turn it into moles using the molar mass, or if it's molarity, using the volume and molarity. Then, of course, the mole ratio comes from the balanced equation back to the mass of product using molar mass. So straightforward stoichiometry goes throughout all chemistry and should be second nature to you by now. Here's a standard stoichiometry problem. The only thing I would suggest you do under testing conditions is that you write down what you're starting with and what you're looking for so that you don't make a silly, careless mistake. And then always check and write those mole ratios. Even if they're 1 to 1, 2 to 2, 3, just write that mole ratio exactly as it is in the balanced equation. The answer you get is your theoretical yield. That's the maximum amount that could be produced in the laboratory. For many reactions, we always, of course, add an excess of one reactant to make sure we react all of the other to get as close to 100% yield as possible. To solve a limiting reactant problem, you need to decide which of the reactants gives you the smallest amount of product. The limiting reactant controls the amount of product. It produces the smallest amount of product. The excess is exactly what it sounds like. It's the amount that's left over. So if you were looking at two reactants being given to you in an equation, you automatically know this is limiting reactant. You take each reactant and solve for the product of interest. There are other ways to do this, but this is the straightforward, clean-cut, not make any careless mistakes method. Again, don't forget your mole ratio between your reactant and your product. Once you're done, you'll have two masses. The smaller mass of product is your theoretical yield, and the substance that makes that is your limiting reactant, and this is your excess reactant. This is nothing. Okay? It's never going to be used again. It just helped you to determine that this was your theoretical yield. The substance that makes the smallest amount, which is the theoretical yield, is the limiting reactant, and the other is the excess reactant. A lot of students will say, this is the excess reactant, or they say that this is the limiting reactant. This isn't a reactant at all. That's your yield. So if copper 2 oxide is the limiting reactant, then to figure out how much excess, we simply use the limiting reactant that we were given and solve for how much ammonia actually reacts with it. So when we do that, we get how much ammonia reacts. To figure out how much is in excess, take the amount you were given and subtract what reacts from it. Just good basic chemistry understanding. What's in the flask, what's reacting, what's being produced. So once you've got your stoichiometry straight, this unit deals with the types of chemical reactions. And in terms of reactions for the AP exam, there's double replacement or precipitate and acid-base, which we know pretty well because we studied those. And then there's redox reactions or oxidation reduction. And that would be your combustion, that would be your synthesis, that would be your decomposition, and it's also all of your single replacement. Your single replacement would have been what we used to make our batteries if we had had the chance to finish out the year. We use that transfer of electrons and capture those electrons and use them for energy. But if you're not a precipitation reaction or acid base, chances are you are a redox or oxidation reduction reaction. So precipitation reactions would be most likely where you'll be asked for your net ionic equation, but you could be asked for any net ionic equation. So precipitation reactions, okay, using your net ionic equations involve some pretty basic rules. Your solubility rules is that all group 1 or alkali metal compounds are soluble. All nitrate compounds are soluble. All acetates are soluble. All ammonium compounds are soluble. So actually, I believe in the new exam, this rule and this rule may be all that's required, but certainly knowing that all acetates and all ammonium compounds are soluble is also quite helpful. Most chlorides are soluble except for silver and lead too. And all transition metal hydroxides are insoluble. So these are solubility rules we've used all year long. They're pretty limited. You should be able to write net ionic equations with those few solubility rules for your double replacement reactions. For other net ionic equations, if it's acid-base, write all strong acids as completely ionized. Write all weak acids as molecules. Write all strong soluble bases as ions. So any group 1 hydroxide, since group 1 compounds are soluble and hydroxides are strong bases, your soluble strong bases are group 1. So write your sodium, potassium, lithium hydroxide as ions, and your weak bases, ammonia and all derivatives of ammonia, as molecules. And then please don't ionize water. When you're thinking of water acting as an acid or base, it's when it's in the presence of an acid or base. And then it's either a proton donor or a proton acceptor. But the molecule water is written H2O. Do not ionize it by itself. So when you're writing your net ionic equations, you have a molecular equation. Anytime you're doing stoichiometry, please use a molecular equation. That helps with your balancing and your molar mass. There's nothing wrong with the molecular equation. It shows good chemistry. A complete ionic equation shows that you know your solubility rules. You know that potassium chromate would be soluble because potassium compounds are soluble, and that barium nitrate would be soluble because all nitrates. And then over here, if one of these isn't a precipitate, it's not going to occur. And all reactions occur on the exam. So since you know that potassium and nitrate ions are spectator ions, the chromate, barium chromate, has to be your insoluble compound. So by the time you cancel out your spectator ions, these are ions that are on the left and right-hand side. They didn't change their identity. They don't react. They're still floating in the beaker, but they don't react. And then you're left with your net ionic. We did so many of these that by now you should be able to look at the formula of the net ionic equation and break the ions down with the correct charges. The biggest mistake for net ionic equations is not getting the charges, and then not making sure that you're balanced for atoms and charges. Remember, if you can't show on the exam that you know what a species is, you honestly don't deserve credit. If you're going to write barium as Ba and you don't know the difference between the ion barium and the atom barium, that's a pretty big gap in your chemistry knowledge. So make sure if you're writing ions, you're putting charges down and that you're writing their correct formulas. So you could take the molecular equation of silver nitrate and hydrochloric acid. You could then ionize it forming the insoluble silver chloride. You could cancel all the spectator ions and you would be left with your net ionic. Or if you really get what's going on, you could write your precipitate and then go back and write your ions that make it up, and you've done that double replacement in a much shorter length of time. So if you were to look at a double replacement, you're looking at a precipitate reaction. If you've got lead 2 nitrate and potassium chloride, 2 solutions of compounds are going to give you a double replacement. You're going to get lead 2 chloride and potassium nitrate. Since potassium and nitrate ions are the spectator ions, your precipitate would be lead 2 chloride, and you could identify that precipitate and write the net ionic. Your precipitate here would be iron 3 hydroxide. You should see that very quickly. You could write your formula for iron 3 hydroxide and then write the ions that make that precipitate. Here, you've got lead 2 sulfide as one product and ammonium nitrate as the other. Your precipitate has to be lead 2 sulfide because ammonium and nitrate would be spectator ions that would not end up in the net ionic. In a net ionic, you cannot leave the spectator ions in there. You cannot write them and then draw a line. You have to not write them at all. Silver nitrate and potassium chromate would make silver chromate because all nitrates and all potassium still would not be in the net ionic. Your acid-base reactions are terminology for acids and bases. If you have a monoprotic, you have 1 hydrogen, di- and triprotic acids. Remember, acids release their hydrogens 1 at a time in a series of reactions. When you're writing the hydronium ion, you sometimes will see it abbreviated as the H+, but of course there's no such thing as the H+ ion. So it's best if you write it as the hydronium ion. Your Bronsted-Lowry definitions are definitely still in this unit. So your acid is a proton donor and your base is a proton acceptor. So in this reaction, following what you see on the right, the HCl donated the proton to the water, making the hydronium ion and leaving you with the chloride ion. I don't know if conjugate acids and bases were in this earlier section. I do not think they were, but of course by now you should know this was your conjugate acid and that's your conjugate base. Here you've got water acting as the acid. You can see that it donated the proton to form the ammonium ion. So this is your acid, this is your base, and your conjugate acid and conjugate base. So when you do acid-base reactions, you make salt and water. So if you're writing the net ionic equations, for a strong acid, you would ionize your acid, and for a weak acid, you would not. Your potassium hydroxide is a strong base in both reactions. You're going to make a soluble salt in both reactions. And then, of course, you're going to write water as a molecular compound. When you cancel out your spectator ions, in the first reaction, you're going to simply be left with H+ and OH negative gives you water. In the second reaction, you're going to have the hydrofluoric acid not ionized, so the fluoride ion would appear on the right-hand side. So the difference in the net ionics is pretty straightforward. For strong acid, strong base, it's H+ OH negative yields water. For weak acid, you're going to have the non-ionized acid. Your hydroxide is still ionized. Your F negative, of course, is going to remain an ion over here because of the soluble potassium fluoride, So there are your net ionics, very clear between weak acids and strong acids, and really important chemistry. That shows you understand what is going on with those species as they ionize. So strong acid, strong base, and weak acid, strong base. So make sure you're ionizing and putting correct charges on all of your ions. If you ionize a weak acid, you've just thrown points away. And if you don't ionize your strong acid, you've thrown points away. So there are 2 videos to watch that I've posted for this review session on net ionics for double replacement and acid base and single replacement. I would take the time to watch those and review your net ionics. One thing that I want to remind you of is that you can create acids with your nonmetal oxides and water. So you easily can get carbonic acid and sulfuric acid by reacting those. Notice carbonic acid would not be ionized because it's weak. Sulfuric acid would be because it is strong. I disagree. This is a little simplified, but actually it would form, you don't ionize H2SO4 in one step. It would be H plus HSO4 with a -1 charge. It would form the bisulfate ion first. When you react the hydroxide ion with any acid, it's going to take the reaction to completion. It's going to rip the proton off of any acid, so don't think there's any different chemistry, okay, in terms of how many moles you're going to add to a weak acid or strong acid if they're monoprotic. There's not, but how that chemistry is written is different. So in your titration and analytical procedure that you've done numerous times, okay, you're going to analyze the concentration of an acid or a base by reacting it with a standard solution. And that standard solution has a precisely known concentration. So the key terms are titrant. That's the solution that you know the concentration of. That's what's in the burette, usually the base, but you can put the acid in the burette and titrate the base. You've done that before as well. The analyte is what's being analyzed. The equivalence point is when you have added the stoichiometric amount. That is the math amount, equal moles. The end point is when the indicator changes color. So your end point better match your equivalence point so that you know you've reached that equivalence point when your indicator changes color, but the terms are slightly different. The equivalence point is the mathematical stoichiometry point, and the end point is when the indicator changes color. So when you're titrating, you want to make sure that you know that you are reading from the bottom of that meniscus and that you are reading down. You are not reading this as it is holding a container full of liquid. It's a delivery device. So they often, as you've had several FRQs, having you read that volume correctly. Making sure you're reading it from the bottom of the meniscus and you're reading down. In a titration, and the last time we did some of these FRQs in class, or it was probably on a Zoom meeting, several of you were doing some really weird things with your reading of your burette. You know who you are, Ashley and Mason. But make sure that you know how to correctly read a burette, okay, from that bottom. The delta V, or change in volume, is always what you're interested in. So it's always the final volume minus the initial. The initial volume is always going to be a smaller number. When you fill the burette all the way up to the top, it's got a 0 volume. So it doesn't make any sense to do initial minus final and then change the sign or whatever it is you're doing. Final minus initial. Final minus initial. You're looking for that pale pink endpoint, so that's a lab skill. Even though that bright pink doesn't look great, it's probably only 1 drop or 1/20th of a milliliter in error. So when you're doing a titration calculation, if you have a monoprotic acid and a base with 1 hydroxide, your mole ratio is 1:1. So it's very easy to simply write MAVA as MBVB. If you're going to use this equation, please label them as acid or base. Don't just write Ma and Va. This is like your dilution equation because the idea is the same. The moles of acid and the moles of base are equal when you reach the equivalence point. When you reach the equivalence point, these are gone. So you added equal moles, and since the mole ratio is 1:1, this setup works beautifully. So just make sure you're plugging your values in. Remember, when you're using this equation, it doesn't matter if you're using milliliters or liters because the units will cancel and you will have your molarity. So if you're going to use this, just make sure you're labeling everything for the reader so they know you know what you're putting in there. If it is not a 1:1 ratio, do not use MAVA. That's not going to work for you. Some of you are going to be able to say, well, I know I'm going to put a 2 here or a 2. Don't do that. That's not likely to get you credit. It's one of their pet peeves. So if it's a reaction that has a mole ratio that's not 1:1, just use stoichiometry. Just use stoichiometry. So if we were to use stoichiometry, we've got 50 milliliters of calcium hydroxide, and we're titrating it with 10 milliliters of 0.1 molar HCl. What's the molarity? So we've got this 10 milliliters of that. We can turn that to moles, and we can say our 2:1 mole ratio, and then use our 50 mils. So let's look at that. There's our 10 milliliters of HCl. There's the molarity of our HCl. Remember, volume times molarity is always moles. So if you want to use the molarity equation here, that also would be fine. Just make sure that you get this in liters. It's important that you show that mole ratio. And then once you get the moles of that calcium hydroxide, then divide it by its volume and get its molarity. That's just good stoichiometry. If you were using a diprotic acid, it would be the same thing. Don't use MAVA. Use your stoichiometry. Take your volume of your acid and its molarity, and you can do this for your monoprotic acids as well. Nothing prevents you from using stoichiometry for all acid base and all solution chemistry. It's the best and safest way. It's just that MAVA is fast and quick if it's a 1:1 ratio. Notice here, for 1 mole of sulfuric acid, it's 2 moles of hydroxide. And then once you get your hydroxide, divide it by that volume, and you've got your molarity. Your titration curves, you should know those by heart. Here's your starting pH. Here's your equivalence point, and there's your excess, and of course, there's your half equivalence point. I don't think that's going to be on your exam because I don't think that is in the first early chapters on acid and base, but it certainly doesn't hurt to look at that and review it. For your pH indicators, you are looking for an indicator that changes color right at plus or minus 1 of that pH value. So your equivalence point is when you have an equal mole amount, and your indicator change should occur right at that point. And your indicators are usually good for plus or minus 1 unit above and below that pH. So now we're at the oxidation reduction reactions. So for these, you want to make sure you can assign and determine an oxidation state. So let's review the rules. The oxidation state of an atom in an element is 0. The oxidation state of a monoatomic element is its charge off the periodic table, nitrogen -3, lithium +1. Oxygen is always a -2 in covalent compounds, except in peroxides where it's a -1. So you have to pay attention. If you think you have a peroxide, double check, and you would have a -1. Hydrogen peroxide is the most common, H2O2, that you will get that -1 charge. Hydrogen is a +1 in covalent compounds. Fluorine, your most electronegative element, is a -1 in your compounds, all of them. Your oxidation states in a neutral compound is 0, the sum of them, and the sum of the oxidation states in an ion is the charge of the ion. So you absolutely need to be able to find oxidation states. I think you had quite a bit of practice in this. If you look back in your notebook, you had some review where you had to find oxidation states of numerous compounds. So when you're looking at any reaction that's considered redox or oxidation reduction, you're looking at a change in that oxidation state. So here you've got a neutral metal with a 0 going to a +2 oxidation state in the formula magnesium chloride. So it's pretty easy to quickly see that you have an element turning into a compound, you have a compound forming an element. That's your first hint that it's oxidation reduction. Even if they don't ask you the charges on that, it's oxidation reduction. So electrons are transferred and oxidation states change. In acid base and double replacement, oxidation states do not change. Therefore, they're not redox. In synthesis, decomposition, and single replacement and combustion, they do change. Okay? Aluminum goes to a compound. The compound iron 3 oxide goes to an element. You've got two elements going to a compound. So anytime you have this change of element to compound, electrons have been transferred and the oxidation states have changed. So zinc has gone to zinc 2+, H+ has gone to hydrogen. So redox, that's a redox reaction. Zinc and oxygen forming a compound. You've got neutral zinc turning into a +2. You've got neutral oxygen turning into a -2. Anytime you have combustion, your oxygen in its elemental form has entered into compounds, so it has formed charges from a neutral oxygen. So it is undergoing oxidation reduction reaction with the fuel. Same thing with this simple combustion reaction. So the original definition of oxidation was reacting with oxygen, and if you react with oxygen, it's still oxidation. So if you were looking at this, you would say iron's been oxidized. Even in first year chemistry, you formed iron 3 oxide. Okay? Your oxidation states, okay, have gone from a 0 from iron as a free element into the +3 charge that came from the formula of iron 3 oxide. In order for iron to form iron 3, it has lost electrons, as most metals do when they form compounds. It has become positively charged, as metals are, and it has been oxidized. Okay? Oxidation is always the loss of electrons, so metals are easily oxidized. When a free metal, meaning a non-bonded metal in its elemental form, forms a compound, it is oxidized. Its oxidation state becomes more positive, but it doesn't have to react with oxygen to become oxidized. Notice potassium has been oxidized as it formed the +1 ion. It still follows the rules. It has become more positive. It has undergone oxidation. Metals, when they form compounds, are oxidized. When O2 formed O2 negative, it gained electrons to become negatively charged. It had a 0 charge here and a -2 here. I noticed that some of you, so when you're writing an element, putting a 0 above the metal is nice to remind you. You don't do that when it's a compound like O2. There's no reason to write a 0 above that, and please don't do that. That just looks weird. It's only above a metal that you put that oxidation state 0, and it's not required. It's just kind of keeps track. So when you have gained electrons, you're going to become negatively charged. That's pretty much common sense, guys. So oxygen has been reduced. Its charge went from 0 to a more negative charge. That's a reduction of charge. Reduction is gaining electrons. If you gain negative charge, you're going to be reducing your charge. If O2 is a reactant, it's always going to be reduced because it is the oxidizing agent for the metal. So if O2 is a reactant, it's going to form probably a compound with that metal, and as the metal becomes oxidized, the O2 becomes reduced. Reduction was originally defined as the removal of oxygen from a compound. Still true. So, in the simple reaction, the oxidation state of iron became more positive. That means it was oxidized. Okay. The oxidation state of oxygen became more negative. That means it was reduced. Oxidation is an increase in the oxidation state. So notice metals become oxidized when they form compounds, and nonmetal elements become oxidized when they form elements because they are negatively charged. Nonmetals are negatively charged. When they form elements, they will go from a negative to a 0, so they will become less negative, while metals will become more positive. So anytime you are increasing your oxidation state, you are becoming oxidized. Reduction is a decrease. So zinc has been oxidized while chlorine has been reduced. Oil rig is a nice way to keep track of that terminology and that transfer of electrons. Oxidation is loss of electrons, reduction is gain. So all your redox reactions can be thought of as happening in two halves, and you have to be able to write half reactions. One half loses, the other half gains. So if you were to write the sodium and chlorine forming sodium and chloride ion, the sodium going to the Na+1 is the oxidation half reaction, and the chlorine is the reduction half reaction. So sodium has been oxidized and chlorine has been reduced. But you have to add those electrons in the half reactions. So here you have an oxidation, and here you have a reduction. So when zinc went to zinc 2+, oxidation is loss of electrons. The electrons have to end up on the right-hand side. That's a product, that's a loss. Those same electrons are the ones that the hydrogen ion gained. So reduction is a gain of electrons. So you have to include those electrons, and in a balanced equation, the electron transfer has to be equal. Zinc was oxidized, copper was reduced. Again, a nice equal transfer of those electrons. If someone were to ask you how many electrons were transferred, you would say 2, not 4. These electrons are those electrons. You can't have oxidation without reduction taking place. Something has to take those electrons from the zinc. Copper, again, has been oxidized, and silver is reduced. Notice here, okay, the silver, we've had to add that 2 to balance the half reaction of silver. So if you had a fancier equation that you had to balance, and we did some of these, where you had to balance all the elements except hydrogen and oxygen, and then you balanced oxygen by adding water, and balanced hydrogen by adding H+, and then added electrons, you're not going to have to go through anything like this from scratch. But you could be given something like this. And if you haven't had an opportunity to balance something all the way from scratch, you might not understand why there are hydrogen ions in here at all, or why there's water. It might confuse you, but remember, you're balancing this redox equation in acid, so you had to add the hydrogen ions. What they might ask you to do, if giving you these, is to balance them for charge and for electrons. So you notice this reaction lost 2 electrons, while this half reaction gained 5. So you would be expected to know that you multiplied the top reaction by 5 and the bottom by 2 to get that 10 electrons that were transferred. So while you would not have to go all the way through, please know that you should be able to recognize what's going on here. You should be able to say that manganese was reduced by figuring out that this is a +7 charge on the permanganate ion. And if you can't do that, go back and review. Okay? So being able to add them up and look at the charge, decide what's been oxidized and reduced, but you probably will never have to go on the exam all the way through that adding of the H+ and the water and so on. It's just too time consuming. So when you titrate with redox, you're so used to titrating acid-base. This would have been one of the other last labs that we did in our electrochemistry study. You can often titrate a reaction. So here's another typical redox reaction. And if you look at it, it looks very familiar. Somewhere along the line, they were titrating and had to do this in an acid solution, and there's their waters to balance. But any reaction that involves oxidation reduction, if you have a color change because of the change of the transition ions, excuse my pointer there, your manganese ion in the +7 is purple, and in the +2 it's colorless. So you can use the color change to monitor this reaction. You don't need an indicator. As soon as you use up all of the +7, their limiting reactant, then you have no color, and you add another drop of that, just like you do with indicators sometimes, and it turns a pale pink. You know that your reaction is done. The only thing different with a redox reaction is that you've got to look at the stoichiometry. So it would be nothing more than a stoichiometry reaction using a redox and a titration. So it might be confusing if you had not seen one, and we will certainly do one in our practice FRQs. I don't like doing them because the cleanup is a pain in the neck, but I think they're important. You fill the burette with this deep purple permanganate that takes forever to clean out of the burette. Then you drop it in, and it does turn purple, and that purple fades away as it becomes the manganese 2+. Once you add enough of that, the purple color will remain. Get a pale pink. So this is the end of all of the material in Unit 4. So I think we can go through Unit 4 pretty quickly in our review, but I do want to devote a significant amount of time to that basic stoichiometry that some of you still struggle with or need to review. because that certainly goes throughout all of chemistry.